Hello, everyone. My name is Zymaková. I work at ELI-Beamlines in the Department of Structural Dynamics. I'm taking care of the development of the X-ray spectroscopy endstation, and today I would like to tell you about the current status and further perspectives of the X-ray spectroscopy user endstation at ELI-Beamlines. But before I start my presentation, let me thank the organizers of this conference and also to all of you who joined this session. So let's get started. Here in this picture, you can see the research campus in Dolny Břežany. And here on the left side, you can see Highlights, a research facility with which we have been intensely collaborating. And on the right side, you can see ELI, that contains the office building, the laboratory building, and the laser building. And in total, it houses around 360 employees. On this slide, you can see a general layout of the facility. And on the first floor, we're having support rooms. In the ground floor, lasers are located. And the radiation of these lasers is being transported in the beam transport in vacuum downstairs to the basement to the experimental halls. Today, I'd like to focus your attention on this part, which is the development of L1 Allegra laser and E1 experimental hall, where the L1 radiation is being utilized. In the right side of the slide, you can see the key parameters of L1 laser. The peak power will be 5 terawatts, the target pulse energy 100 millijoules with the pulse length of less than 20 femtoseconds with the reverberation rate of 1 kilohertz, and this laser is an in-house development of ELI-Beamlines. Here you can see E1 experimental hall, how it is now. So basically, Allegra beam transport the laser from upstairs, and in the vacuum system, it is transporting the laser to the secondary sources, which are HEG, high harmonic generation, and few plasma X-ray sources. And then the radiation of the sources is utilized at the MAC station for AMO and coherent imaging, and the plasma X-ray sources are used for X-ray spectroscopy and X-ray diffractometry. So basically, in this experimental hall, we are also using support lasers, which are having different parameters but the same wavelengths as L1 Allegra laser. The X-ray science is then housed here in this in this blue X-ray hatch. What I will be speaking about today will be everything that is happening here in this small blue room. In this slide, you can see a list of our X-ray sources for the X-ray end stations. So we are having inside the hatch 2 conventional X-ray tubes and 3 plasma X-ray sources. Let's say the metal jet plasma X-ray source is still currently under development, so it has been temporarily placed to another experimental hall. And in E1, we are having the copper tape plasma X-ray source, which has been delivered and installed and is pending commissioning in July 2021, so very soon. And the pulsed radiation is like another source of the pulsed radiation is the Waterjet plasma X-ray source. This is fully functional. It has been adapted to the ELI high power lasers by our collaborator Jens Uhlik from Lund University from Sweden. Here you can see a layout of the copper tape plasma X-ray source. So in a nutshell, a laser beam is focused by a focusing parabola, and it is transported through an optical window into a separate vacuum chamber, where the laser beam is interacting with the copper tape. The copper tape is running between 2 rolls. And also we are having 2 additional tapes for debris handling, this one and this one. So on the right side of the slide, you can see the X-ray spectrum of the copper tape plasma X-ray source. And as you can see, the characteristic lines are located around 8 and 9 kilo electron volts. In the next slide, you can see a layout of the wire jet plasma X-ray source. So basically, again, the laser beam is focused by a focusing parabola inside a vacuum chamber. This small and compact vacuum chamber locates a wire jet target, which is surrounded by a catcher, also for handling of the wire debris. And the plasma interacts with the water, creating Bremsstrahlung radiation, which is emitted in 4pi, and then part of this radiation is being focused by a polycapillary, which predetermines the direction of the X-ray beam. Basically, here you can see a picture of the water jet plasma X-ray source. You can see a very compact vacuum chamber. And you can also see here results of our experimental run with the L1 Legend laser. So on the left side, you see a result of a direct X-ray absorption spectroscopy detection. And you can see the absorption edge here. The sample was a copper foil. And then on the right side, you can see the achieved photon flux with the L1 laser being run at around 11 to 12 millijoules at that stage. The experiment was performed in autumn last year. In the next slide, you can see a layout of the X-ray spectroscopy endstation, which is built in von Hamos geometry. So basically, this geometry is prototyped by the spectrometer in the laboratory of Professor Jakub Szlachetko in Krakow, in Poland. So as many of you know, the von Hamos geometry includes a triangle which is created by a sample, a focusing crystal, and a CCD. Here in this layout, you can see the geometry in the emission. Scheme. However, at the end station, we are having two CCDs, so basically both emission and absorption can be performed at the same time, simultaneously. In the middle of the slide, you can see the picture of the end station, and this is basically our offline station for sample pre-characterization, so it utilizes an X-ray tube radiation. And then again, a sample, focusing crystal, and the detector. And on the right side, I'm happy to show you the results achieved by this offline sample pre-characterization station. So basically, first, calibration iron foil was measured, and with the black, you can see the curve of K-alpha 1 and K-alpha 2 emission lines, and the colored curves are actually the characteristic features of the iron hexacyanophorate aqueous solution, which was delivered by a wire-guided sample delivery system. And basically, we measured this solution in different concentrations. And the count rate of every of these curves corresponds to 2 hours acquisition time, but different concentrations. We are preparing a paper on this end station, so I hope it will see the world soon, and then you are all very welcome to read it. And here you can see the current status of the X-ray spectroscopy station. So basically, we are preparing a pump probe experiment within the Visegrad collaboration. We are actually having the third round of this collaboration, which has been very successful. Within this collaboration, we have created a CELIX. This is a consortium around ELI for X-ray spectroscopy. And I would like here also to mention or to acknowledge the support of the Visegrad Fund. So basically, this experiment is planned for September with the copper tape plasma X-ray source. And here you can see a beam transport of the pump beam. and the copper tape source which has been installed. So in case of your interest, here is a list of contacts of my colleagues who are working at different stations, who are taking care of different stations. Please feel free to contact them in case you have got any interest or you have any questions about the end stations or sources. They are very open and would very happily answer your questions and contact with you. With this, I would like to thank you for your kind listening.